Hello, this is Dr. Bramall. This is a recording made for Bio 100 at Eastern Kentucky University. I'm recording this on March 19th, but this is actually for our, this would be the lecture that I would have given on March 20th in our Introductory to Biology class for non-majors. So our goal today is going to be to pick up where we left off on Monday, talking about the Hardy-Weinberg equilibrium. And we introduced the Hardy-Weinberg equilibrium on Monday as a method to tell whether or not a population is evolving. Now, it is going to be important, both in lecture and in lab, that we understand the math that's involved in the Hardy-Weinberg equation. It's very simple. I'm going to explain it over the next few minutes. Some of you will have already encountered it. Those of you that had lab yesterday, or actually today, the 19th, or perhaps have lab before you actually listen to this recording. But this will be a brief explanation of what you need to know for both lecture and lab regarding this equation. So briefly, if you follow the cursor on the screen, then I'm pointing to this particular equation, and we realize that the Hardy-Weinberg equation is shown here on the screen. Perhaps I should first say that the Hardy-Weinberg equation is an equation that has been developed by ecologists that allows us to tell if a population is evolving or is not evolving. And so that's its origin. And this is the actual equation that we see on the screen. P squared plus 2pq plus q squared equals 1. So of course that means nothing to you at this point, but let me explain over the next couple minutes how we use this. And so interestingly, p squared, the term we see at the very beginning of the equation, is going to represent the frequency of homozygous dominant individuals in the population, as it says here, just beneath our equation. 2pq, as we see in the next line, is going to represent the frequency of heterozygotes in the population, and q squared is going to represent the frequency of homozygous recessive individuals. It's going to be most useful to look at an example in order to understand this. This is what I typically do on the board in class, and so I've added this slide. Let me advance to this slide. Bit of technical trouble here. There we go. Advance to this slide to explain this particular equation. Okay, so we can only use the Hardy-Weinberg equation to look at one single set of alleles at one time. Just one set of alleles. And so we could look at hair color, assuming hair color is controlled by one gene, which is not always realistic. Or we could look at eye color, or we could look at skin color, assuming all those traits were controlled by one gene, which, as you know, is not often the case. But the Hardy-Weinberg equilibrium only lets us look at one set of alleles at a time. So let's go up to the top of our screen here, and what I have at the top of the screen, here's my cursor, and if you follow the cursor, then you see that I have a hypothetical population that we observe in the environment. And so if we look at the top line of the screen, we see that in this particular population, we have a total of 25 individuals. 10 of those individuals are homozygous dominant, as we see here. 7 of those individuals are heterozygous, and 8 of those individuals are homozygous recessive. So that's easy enough. All I'm saying is we go out into the field, we collect a bunch of organisms, and we say, let's say that they're rabbits. And some of them have black hair and some of them have white hair. We collect 25 rabbits, we do a genetic test to see which alleles they possess, and we come to this conclusion. 10 are homozygous dominant, 7 are heterozygous, and 8 are homozygous recessive. Okay, some simple math begins at this point. The question is, in this population, how many dominant alleles do we have and how many recessive alleles do we have? We can easily calculate that by simply starting here at the left-hand side and saying, all right, so we have 10 individuals that are homozygous dominant. And ask yourself this question: how many alleles does each of those individuals possess? How many dominant alleles? And the answer, of course, is 2, right? We can see it plain as day. If you're homozygous dominant, on each of those homologous chromosomes, you have a dominant allele. So 2 times 10, of course, is 20. And then we have to ask ourselves the question, in this population, are there any other individuals that have a dominant allele? The answer, of course, is yes, the heterozygotes. But each heterozygote has how many dominant alleles? And of course, the answer is 1. Each heterozygote has 1 dominant allele and 1 recessive allele. So if we take the 20 dominant alleles that are possessed by the homozygous dominant individuals and add that to the 7 alleles that are possessed by the heterozygous individuals, then we get 27. So simple math there. And so I have 27 written in the line below it. We have a total of 27 dominant alleles. And then we do the same thing for the recessive alleles. We can see that we have 8 homozygous recessive individuals. 8 times 2 is 16. Once again, we have 7 recessive alleles in those heterozygotes. And so 16 plus 7 is 23. So we have a total of 23 recessive alleles. And so for the total number of alleles, we have 50. 27 plus 23 equals 50. Of course, we know that because we had 25 individuals in the population, and each has 2 alleles, and so we have, of course, a total of 50 alleles there. All right, so the simple math continues. Hopefully that was fairly self-explanatory, or at least you understood that explanation clearly. So we now need the allele frequency. Piece of cake to calculate. The question simply is this: what percentage of the alleles in the population are dominant? And so the answer is 27 out of 50. How do you turn that into a percent? Well, you put 27 over 50. Divide 27 by 50. If you do that, you get 54%, and we express that as a decimal here, so we have 0.54. So that was easy enough. The question then becomes, how many recessive alleles do we have in the population? Or rather, actually, let me correct myself, what percentage of the alleles in the population are recessive? We answer that by saying 23 divided by 50 is 46. We express that as a decimal, so we have 0.46. Now, the rest of this becomes very, very easy. We have our P and we have our Q. If you go back to the first slide, you realize that P squared equals the frequency of homozygous dominance, 2PQ equals the frequency of heterozygotes, and Q squared equals the frequency of homozygous recessive individuals. I may have omitted adding this, and so let me add it, or at least re-add it if I repeat it if I've already said it. We're going to always say that P equals the frequency of the dominant allele and Q equals the frequency of the recessive allele. If we simply remember that, then everything will make perfect sense. So to plug these P and Q into our equation, we just have to take 0.54 squared, which I have done here. 0.54 squared equals 0.29. All right, and then it's just a matter of plug and chug here. So we put in 0.54 for P right here, 0.46 for Q. 2 times 0.54 times 0.46 equals 0.50. If you do that math, that's what you'll get. Q squared equals 0.46 squared, which equals 0.21. We can double check ourselves by seeing if our math adds to 1. 0.29 plus 0.50 plus 0.21 does indeed equal 1. And so then the question is, what have we done? What does this mean? And so if you go back to the previous slide, then you realize that what we have calculated, P squared, is the frequency of homozygous dominant individuals in the population. So that means that 29% of the individuals in the population will be homozygous dominant, 50% will be heterozygous, 21% will be homozygous recessive. And so the last step is to say, what are the actual numbers that we see of each of these categories in the population? That's easy to get. So all we have to do there is take the total number of animals we have, and remember that's 25, and so if we take 0.29 times 25, we get 14.5. That means that if the population is in Hardy-Weinberg equilibrium, we will see 14.5 homozygous dominant individuals. And again, if the population is in Hardy-Weinberg equilibrium, 25 heterozygotes and 10.5 homozygous recessive individuals. So then this makes a lot of sense, right? So we just take our expected values, which we have calculated here. All right, so I have to make a small apology here. I have done these numbers for 50. So in reality, I should have taken 0.29 times 25. And if I had done that, then I would get this number here. So sorry, everything I told you is correct, but I accidentally multiplied these percentages by 50 because I was thinking there was 50 animals in the population. So all we have to do then is remember that if we take 0.29 times the total number of animals, 25 in this case, then we get our expected value, which I do have the correct value down here. It's 7.3. We expect to see 7.3 homozygous dominant individuals, 12.5 heterozygous individuals, and 5.3 homozygous recessive individuals. Again, I apologize. The only mistake that we've made here that I have made is